Continuing with the lecture for semester 4 of paper 9, elements of modern physics. I will just move ahead with the physical interpretation of psi, which is the part of the syllabus. Although we are discussing quantum, but it's not a quantum, it's a modern physics. So we'll confine our discussion as per the syllabus actually. So what we know is that in a light wave, the electromagnetic field, it varies in space and time. Okay, so in the light field we know like this. I mean, in a sound wave, basically what we can say is that the field, or the pressure wave rather, it varies in space and time. Now what is it that whose variation constitutes de Broglie waves? Now this is a very important question. Okay, so the answer is that the variable quantity psi, the variable quantity psi called wave function characterizes the de Broglie wave. Okay, now more precisely what psi is, this may be one of the questions. So one thing is certain, that psi must be in some sense be a measure of the presence of particle. Okay, now but the function psi as a function of x comma t, okay, in general cannot be direct measure of the probability of finding a particle around a position, okay, at time t, because of, if that is the case, it should be positive and real quantity. But in general, psi is basically a complex function. So in physical optics, though the interference patterns are produced by the superposition of the wave, okay, E and H, okay, but the intensity of fringes, it is measured by E naught square, which is the square of the amplitude. Now truly speaking, it will be something like this, that E plus E, the conjugate, and E plus E. Now this, the multiplication of this will give you 4 mod of E square, that is 4 E naught square. Now in analogy to this bond, he assumed that the positive quantity psi asterisk into psi dx dy dz, which is equal to psi, which is obviously a function of r comma t, into d tau. It measures the probability of finding the particle. Now this measures the probability of finding the probability of finding the particle in the given volume. Okay, volume element d tau, which is equal to dx to dy into dz, about the point r at time t. Okay, so now psi mod of psi square, it is called the position, probability density. Now what basically it means is that suppose if at any time we have psi, okay, as a function of r comma t mod square d tau equal to half. Now what does it mean? It means that according to the assumption, the probability of finding the particle around the point r in volume element d tau is half. Now this, however, does not mean that the volume has half the particle. Okay, basically the physical meaning of the relation is that if the experiment is performed a large number of times, say n number of times, okay, so then a number of times a particle will be found in the volume element d tau, okay, around r at time t is n by 2. So at the point where psi is equal to 0, okay, the probability of finding a particle is also 0, and at point where mod of psi square is non-zero, the probability of finding the particle is non-zero. So for a system composed of only one particle, the total for a system composed of only one particle, Okay, the total probability of finding the particle anywhere in the space at time t must be equal to 1. Okay, so it could be something like this: minus into plus infinity, again minus into plus infinity, again minus into plus infinity, integration psi hot psi square d tau must be equal to 1, where the integration is over the entire space. Okay, so a wave function satisfies this condition. A wave function satisfying the above condition, let this be equation 1. Okay, above condition is called a normalized wave. Okay, so the wave function psi for which integration of mod psi square deta exists is often called a square or a quadratically integrable, right? So if we proceed further with this relation, okay, what will happen is that the statement it's given by equation 1. Okay, we already have this equation 1. The statement given by equation 1, okay, amounts to the fact that the particle is sure to be found somewhere in space. Now this has to be true at all times as long as the particle is stable one, which cannot decay or disappear in some other way. Therefore the total probability must be conserved or should be independent of time, that is del y del t mod of psi square beta must be equal to 0. Now this can be shown in the following manner. We know that the Schrodinger equation I h cross del psi by del t is equal to minus h cross square by 2m del psi plus v psi. So this will be equation 2. Along with its complex conjugate, we'll write I minus I h cross del psi strict by del t equal to minus h cross square by 2m del square psi plus v psi strict. So here also, okay, so this will be equation number 3, where this v as a function of r comma t is assumed to be real. Now multiplying this now we have multiplying this equation number 2 and 3, okay, by psi strict and psi. So and then subtracting the resultant equations, we get I h cross psi strict into del psi by del t plus del psi strict by del t into psi equal to minus h cross square by 2m psi strict del square psi minus obviously del square psi strict into psi. This could be written as minus h cross square by 2m psi strict del psi minus del psi strict, okay, into psi. So this will be equation number 4. Now using vector algebra, what we'll write is that the above equation may be written as del we'll write del rho r comma t, okay, plus del J R comma T equal to 0. This is equation number 5. Now here we will define rho as a function of R comma T as psi asterisk R comma T into psi, okay, alright, psi R comma T, and this will be equation number say 5 or rather 6. Now again J as a function of R comma T may be written as H cross by 2im, okay, psi asterisk del psi minus del psi asterisk into psi. So this will be question number let it be 6a and 6b. Now equation number 5. Okay, now equation number 5 is known as equation of continuity. Okay, equation 5 is known as equation of continuity in fluid dynamics. Okay, now in which rho represents the density of fluid or number of particles per unit volume, okay, and J, here J represents current density, okay. It is therefore reasonable to interpret rho. It is therefore reasonable to interpret rho given by equation number this one. Already we have done. Given by equation rho. I mean equation number 6a. Okay. Equation number 6a. As the position probability density. So equation 6a. It is it may be interpreted to be interpreted as the position probability density in the sense that psi asterisk psi dot t will be the probability of finding the particle in the volume element d tau, and J given by equation 6b as the probability current density. 6b represents the probability here. It's 6a and 6 is very important. 6a, it represents it may be interpreted as the position probability density, okay, and 6b as 6b, okay, it may be represented as the probability current density, which can be written as, okay, J is equal to half psi asterisk H cross by im del psi minus psi H cross by im del psi asterisk. Okay, so this could be further simplified to write it like this: real part of psi asterisk. Okay, this we are using this operator, this one, where V subscript OP, it represents the velocity operator, and RE obviously it stands for the real part of the quantity inside the bracket. So now from this particular equation, from equation 6a and equation number, say suppose this is 7, so equation number 7, one gets J is equal to rho into V OP, okay, which is the same as expression in the case of fluid dynamics, and hence the name current density for J is justified. Okay, now we'll just stop over here the discussion of today's lecture. We'll just continue with this in the next lecture. Until then, thank you.